China's ambitious C949 supersonic jet promises to shatter records and redefine long-haul travel. But can it really outstrip the Concorde in every key metric? Imagine boarding in Beijing at dawn, sipping coffee at cruising altitude, and stepping off in New York just hours later. Jet lag banished, time zones conquered. That vision lies at the heart of the C949 project, which claims not only higher speeds and longer range than the legendary Concorde, but also meaningful advances in efficiency, comfort, and environmental impact. Yet history warns us that raw performance alone cannot guarantee commercial success. The Concorde itself dazzled the world with Mach 2 speeds, yet ultimately succumbed to economic, regulatory, and technical hurdles. As China accelerates toward a supersonic future, it must confront that same triad of challenges: environmental sustainability, economic viability, and market acceptance, while navigating a competitive landscape crowded with both entrenched subsonic giants and nimble supersonic newcomers. Although the Concorde embodied the pinnacle of 20th century aerodynamics and power plant technology, it never achieved practical ubiquity. Its Olympus engines, optimized for twin afterburner thrust, guzzled fuel at roughly 3 times the per-seat rate of today's fuel-efficient airliners. Sonic booms reverberated over populated areas at intensities exceeding 105 dB, triggering international bans on overland supersonic routes. And while its delta-wing design offered stability at Mach 2, that very configuration imposed structural and weight penalties that limited passenger capacity to around 100, ensuring sky-high ticket prices north of $10,000 round-trip. By contrast, modern composite materials and computational fluid dynamics tools were not available in the Concorde's heyday, meaning that its designers lacked the flexibility to shrink weight, optimize aerodynamic lift-to-drag ratios, or model low-boom shockwave propagation with the precision engineers enjoy today. Addressing these historic shortcomings lies at the core of the C949's development. Its projected cruise speed of Mach 2.2, approximately 1,650 miles per hour, represents an 8% leap over the Concorde's Mach 2.04. But speed is only part of the story. More transformative is the claimed nonstop range of over 12,000 kilometers, nearly double the Concorde's 6,580 kilometers. That extended reach would enable nonstop links between Beijing and New York, Shanghai and London, or even Beijing and Los Angeles without refueling stops. Achieving such range hinges on a suite of enhancements: advanced carbon fiber composites that cut airframe weight by up to 25%, adaptive wing surfaces that optimize aerodynamic efficiency at both subsonic and supersonic regimes, and engines with variable cycle capability that adjust internal airflow paths to maximize thrust during acceleration, while reverting to high bypass modes for cruise to conserve fuel. Yet long distance and blistering speed do little good if regulatory and environmental barriers choke off routes. Supersonic overland flight remains prohibited in much of the world due to sonic booms crisscrossing urban landscapes. The C949's designers claim a low-boom airframe profile, sculpting the fuselage and wing leading edges to disperse pressure waves more gradually and reduce the ground-level signature to around 75 dB, a sound comparable to a car door closing. Early wind tunnel and computational studies suggest this soft boom design could satisfy both FAA and ESA noise regulations, opening overland corridors across North America, Europe, and China's populous eastern provinces. However, final certification will require flight test validation and likely new chapters in international aviation law, meaning that political negotiations and community outreach will matter as much as technical success. Beyond noise, environmental sustainability demands that the C949 consume far less fuel per passenger than its forebear. Whereas the Concorde burned roughly 17 liters per seat per 100 kilometers, engineers today target a 30 to 40% reduction in fuel burn through hybrid propulsion concepts, biofuel compatibility, and advanced thermal management systems. The proposed power plant design incorporates afterburning variable cycle turbofans. In takeoff and acceleration phases, a high-energy flow provides necessary thrust, while in cruise the fan bypass ratio increases to throttle back fuel consumption. Parallel efforts to validate sustainable aviation fuels and drop-in biofuel blends will determine whether supersonic routes can fit within global decarbonization targets. especially as the International Civil Aviation Organization pursues net zero carbon emissions by mid-century. Even if environmental and regulatory walls prove permeable, the C949 must confront the formidable economics of supersonic flight. The Concorde's per-hour operating costs exceeded $100,000, forcing airlines to charge exorbitant fares and limiting patronage to an elite few. China's project benefits from state backing that can absorb R&D expenses and provide low-cost financing, but ticket prices will still need to appeal to business travelers and tech-savvy tourists rather than only billionaires. Initial estimates suggest one-way fares might start around $6,000 to $8,000, putting them within reach of upper-tier corporate budgets. Achieving profitable load factors, perhaps 80% or higher, will require careful route selection, dynamic pricing during off-peak windows, and partnerships with global carriers to guarantee strong advance bookings. Market competition further complicates the supersonic landscape. Boom Supersonic's Overture aims for Mach 1.7 service with about 65 seats, while Ariane's AS2 and Spike Aerospace's S512 concepts targeted business jet segments with fewer passengers but lower infrastructure demands. Meanwhile, Boeing and Airbus continue to invest in subsonic platforms like the 787 Dreamliner and A350, which offer extended range, exceptional fuel efficiency, and passenger comfort at lower fares. Airlines may hesitate to swap proven wide-bodies for untested supersonics until reliability data, maintenance costs, and pilot training programs have matured. China's advantage lies in vertical integration across its aerospace supply chain, from raw materials to final assembly, potentially driving down unit costs and accelerating certification timelines. Customer experience represents another battleground where the C949 seeks to outshine its predecessor. The Concorde's cabin felt cramped and noisy, with small windows and limited pressure regulation. By contrast, China's design envisions 120 seats in a configuration that balances density with personal space, noise cancellation headliner panels, and electrochromic windows that toggle transparency to manage glare and solar heating. Climate control systems employing zonal air circulation aim to maintain consistent temperature and humidity, reducing passenger fatigue. Real-time connectivity via high-speed satellite links would keep travelers online at altitudes above 60,000 feet, making those nonstop intercontinental hops as productive as they are swift. Underpinning operations, digital twin technology offers a paradigm shift in maintenance and reliability. For every C949 produced, a virtual replica synchronizes sensor data on engine health, structural stress, and avionics performance, enabling predictive interventions rather than reactive repairs. Airlines subscribing to this model could achieve dispatch reliability comparable to subsonic fleet averages while minimizing unscheduled groundings. Over time, data analytics from hundreds of simulated flight cycles will refine maintenance intervals, further driving down lifecycle costs and enhancing safety margins. Of course, grand claims require empirical proof. The C949 prototypes made in flight, scheduled in the late 2020s, will be the decisive moment when wind tunnel curves give way to real-world turbulence, and a low-boom thump must be measured over American farmland as well as Chinese deserts. Certification processes through the CAAC, FAA, and EASA could stretch across years, especially if agencies demand new noise and emission standards. Geopolitical tensions may complicate joint testing agreements and export clearances, particularly for advanced engines co-developed with Western partners. If the C949 surmounts these hurdles, the ripple effects across aviation will be profound. Airports will need reinforced runways capable of supporting high-temperature exhaust plumes and specialized fueling infrastructure for SAFs. Pilot training academies must integrate supersonic aerodynamics into curricula, and global route networks may polarize between subsonic feeder services and supersonic trunk lines, ushering in a two-tiered system of air travel where speed becomes a selectable commodity rather than a niche extravagance. Ultimately, China's C949 aspires to transcend the Concorde's legacy by delivering not just faster travel, but smarter, cleaner, and more connected journeys. The Concorde taught the world that Mach 2 was achievable. The C949 must prove that Mach 2 can be practical. If it succeeds, it will herald a new era when the planet truly shrinks beneath our wings. where continents blur and time zones yield to the relentless march of innovation. Whether that future arrives on schedule or demands patience, one certainty remains. The race to redefine supersonic travel has entered its most thrilling chapter yet.